This is going to be question number 36. It asks, what is the slope in the xy plane that passes through the origin? By the way, any equation that passes through the origin, it's kind of like direct variation. It's going to have y equals the slope times x. And there's going to be plus 0, but you wouldn't write that. And it's tangent to the graph of the curve y equals x cubed plus 16. Now, while I am very comfortable with the calculus, sort of a flipped around calculus version of this, where you take the derivative, plug in an x value where you want that derivative to be, okay, and then you can tell what the slope is. This is backwards. This is actually saying it wants that tangent line through a different point that's not on that cubic equation graph. So the best way to do this is guess and check, and I'm going to show you what I did here. First of all, I'm going to go into my calculator and I'm going to put this into the calculator, and I should probably go to red because it defaults to red. And so since I always do the graphs in order by color, ROYGBIV, I don't know if I said that right, ROYGBIV, then that's how I can tell what's what. So here's what it's saying. It says, what's the slope of the line? And again, it's y equals mx if it's passing through the origin. And then here are the solutions, the possible slopes. So it's asking you is it y equals 2x? Is the equation y equals 12x? Is the equation y equals 16x? Or is the equation y equals 24x? Now I'm going to tell you that I actually graphed this myself just to try and see if I could eyeball it. Once you get super steep slopes and they're big numbers, it's really hard to tell with a hand-drawn graph. Let me just kind of show you over here what the slope is right there, because when you've got graphs that are spanning large distances on the coordinate plane, there's so much error that you're making in that situation. So I am going to go to technology and use the calculator for this. So let me show you what I did. I'm going to delete these. Delete. Yes, I'm sure. Delete. Yep. Positive. Delete. Okay. So I'm going to first enter in that cubic equation. So it's y equals x to the third power plus 16. I'm also going to, because this is the part of the question, and so it's going to be there for all of them, I'm going to make this one thicker. Then I'm going to add each one of these possible tangent lines. So y equals 2x. RO is next, so orange. RO. I'm going to add y equals 12x. And that's going to be, yellow doesn't show up very well, so I'm going to jump to green. ROIG. And then I'm going to add y equals 16x. And that's going to be a blue. And then I'm going to add y equals 24x. And that's going to be a purple or pink. Okay. All right. Now I'm going to look at the graph, and oh boy. First of all, none of these, a tangent, and let me just give you a by the way, because I don't know how much we've talked about this. A tangent line means it just barely kisses at one and only one point. So if I had like this, a tangent line at that point would just be right there, okay? And the tangent line, the slope of the tangent line is the rate of change, the speed or velocity of the function at that given time. That's the significance of the derivative. It is the slope, which is the rate of change. So, looking back at those graphs, that is insane. And so this is what I'm going to do. I'm going to go in and turn them on one at a time. Go back to the graph. I can see here that I can't see where they could potentially be tangent, so I'm going to have to zoom out. All right, notice this is going to continue going up at a more and more rapid rate, whereas this crosses, but it's never going to hug up and kiss that red function, okay? So it's not y equals 2x, because y equals 2x is definitely not tangent to that red function. So I'm going to turn that off, and I'm going to go look at y equals 12x. This is a maybe. It looks like it's hugging up to just barely. So what I'm going to do is a box, and I'm going to zoom in on this critical area. I'm going to try something because it's kind of hard to see. I'm going to make that one dark too, and then go look at it again. It looks tangent. I'm going to zoom in and make sure, I'm going to zoom in with the box right here and just make sure that it doesn't look like it's crossing at two different places. Okay, because oftentimes a tangent will look so close to the function that it looks like they're traveling on the same line or the same path. I want you to notice there's no separation between them. I think that this particular one is, and option B, is really a very good candidate for tangent, but I'm going to go look at the other two now, and I kind of like the thicker one better. It's easier to see. So I'm going to go look at the graph again. I need to zoom out and see what I'm looking at here. Now you can clearly see here that it crosses and then heads on up. That's not tangent. That's not just barely kissing. That's slicing through. So that is not gonna be your tangent. So I'm gonna turn that one off. C is not the answer. I think, and I hope you're seeing that kind of for obvious reasons, if a more severe slope, the 16, makes it very clear that it's slicing through rather than tangent, then certainly an even more severe slope would probably do the same. So yeah, so let's go look at that. And you can look at that and see that clearly it slices through. It's not tangent to this anywhere, which means looking at these, you can see that the line that was tangent was y equals 12x, so the answer is B.